Hi class, Professor Alberg here again, and we're going to be doing an example of hypothesis testing for a mean. So here's an example. Suppose that you thought that the average salary in your town was greater than 50,000 per year, and you took a random sample of 30 people and found that the sample mean was 56,000 with a standard deviation of 7,000. Can we infer that you are correct, that the true population mean salary is greater than 50,000? Okay, so we have to set up our null and alternative hypotheses. We normally set up the alternative hypothesis first. So we have the alternative hypothesis is what we could possibly infer. So can we infer that it's greater than 50,000? So there we have it. Now, so the null hypothesis is the opposite of that, and it has to contain the equal sign. The reason why it has to contain the equal sign is that we have to anchor our assumption so that we can calculate a p-value. Okay, so the null hypothesis is that it's equal to 50,000. It could be less than or equal to 50,000, but the key thing is that it's equal to 50,000, so I emphasize it like that. The problem does not say what alpha is or the confidence level. So we use 0.05 as the industry standard or default value. So we have to calculate a p-value and then draw a conclusion. But there's also another step that we should take, and that is first we have to see if the sample result could possibly infer the alternative hypothesis, and the sample result is 56,000, which is greater than 50,000, so we could possibly infer the alternative hypothesis. If it was less than 50,000, then we could not possibly infer it, and it wouldn't be up to a p-value. Now, why do we even have to calculate a p-value? 56,000 is greater than 50,000. How come we don't automatically just infer the alternative? It's a key question. The answer to it is that sample results vary, and it is conceivable that we get a sample result of 56,000 even though the true population is 50,000. So we have to see how unlikely the 56,000 is if in fact the 50,000 is true. And if our sample result is pretty likely within sampling chance of getting 56,000, even though it's 50,000, even though we think the mean is 50,000, then we couldn't possibly infer the alternative. Okay, but if it's pretty unlikely to get 56,000, if in fact the true mean is 50,000, then we can say, okay, then it's probably not 50,000, so we reject HO and go with the alternative. So that's the logic of a hypothesis test and everything. So everything's all set. So now we have to calculate a p-value. So let's do that, and let's bring in our trusty calculator to do that, because that's the way we do that. Okay, so we say on, then clear. Now how we do it is we go into stats, so we hit stats, and we go to tests, and it's actually a t-test for a mean, so we go with t-test for a mean. And if we have data, we can put the data in a list and get it, but we can go stats. So the null hypothesis is 50,000, so we can put 50,000. I'm just going to put 50 because the thousands scale out. X bar is 56,000, that's what we got, so 56. The standard deviation was 7,000, so 7. If you put in the thousands, everything would come out the same. The sample size is 30, n, and we do think that it's greater than 50,000, so we'll keep it there. So we'll go down and just hit calculate, and we'll hit enter. And it calculates it. We get a t-stat, a really big t-stat, which is z-score of that. So that's really large, and so that's greater than the critical value, so we can reject HO on that for the classical method. But p-value is a traditional method, is the current standard and for hypothesis testing. So we get a p-value. This is some strange thing, e to the minus 5. So the p-value is actually, let's see, 2.69 times 10 raised to the minus 5. Okay, so that's equal to 0.00004 zeros, 296, three significant digits. Okay, so we basically moved it over 1, 2, 3, 4, 5 places. So that p-value is really small. So the probability of getting this sample result, an x-bar of 56,000, if in fact the mean is 50,000, is really unlikely. So we can reject that assumption and infer the alternative. So since the p-value is less than alpha, okay, and I'll put this in as less than alpha, we reject HO and then conclude there is sufficient statistical evidence to infer that the true population, I'm just going to copy it in, that the true population mean is greater than 50. There we go.